Hello everyone, welcome to this channel. I'm Payman Ansari, and in this tutorial, I'm going to talk about how to implement Principal Component Analysis, or PCA for short, in RapidMiner. Principal Component Analysis is a technique used to emphasize variations and bring out a strong pattern in a dataset. It's a way to simplify complex data by reducing the number of variables while retaining as much information as possible. PCA identify patterns in the data by finding directions or principal components where there is most variation. These principal components are ranked by how much variation they explain. The first principal component explains the most variation, the second explains the second most, and so on. Then it reduces the dimension by keeping only the top rank principal components. Why is it used? PCA can be used for visualization. It can help visualize high-dimensional data by reducing it to 2 or 3 dimensions that can be plotted on a graph. PCA can be used for noise reduction. It can help filter out noise and unimportant information in the data. PCA can be used for feature extraction to create new and more informative features from the original data. Also, PCA can be used to speed up machine learning by reducing the number of variables in the data. So, PCA is a powerful tool for simplifying complex data and finding hidden patterns. The dataset that I use is Iris dataset, and it can be found easily on internet. I put the link to the data in the description. Let's bring the data into the process panel and take a look at the data. As you see, I have 150 data example with 5 regular attributes, where here the class feature is target variable for classification, and we do not use it, so we remove it. Let's take a look at the statistic. And this is the name of the columns. This is the data type. And as you see, all of them are real. There is no missing values. And this is some statistics about each feature. To remove the class feature, we use an operator called select attributes. Bring the select attribute into the process panel. Connect these two operators together and configure this. Attribute filter type is subset, and we choose those attributes that we want to use. Here is the 4 features that we need. Apply. The next step is to normalize the data for PCA. It is crucial to normalize it because if one variable has a much larger range than others, it will dominate the PCA. This means the principal component will be heavily influenced by that variable, even if it's not the most important one for understanding the underlying pattern. To normalize, we use normalize operator. Bring the operator into the process panel, connect them together, and configure this one. Attribute filter type, I'm going to use all because I want to normalize all of them. And the method, I use z-transform, where the average would be 0 and a standard deviation for each feature would be 1. There are other type of normalization that can be used as well. Next, I'm going to apply principal component analysis by using PCA operator. So this is principal component analysis operator. Bring it into the process panel, connect two operators together, and configure this. For the dimensionality reduction, we have different options. If I choose none, all of the principal component will be created. The maximum number of PCs equals the number of original variable in the dataset, and you can decide how many of them you want to use. If I choose this one and connect it to the output, because I have 4 variables, then I will have 4 principal components, PC1, PC2, PC3, and PC4. Let's go back. And if I choose keep variance, then I need to pick a variance threshold. And this threshold is a number between 0 and 1. And all components with cumulative variance greater than the threshold will be removed. Let's choose, for example, 90.9. And if I run the process, I will have only 2 principal components. Another option is to use a fixed number where you need to choose a number of components you want to use. Let's pick, for example, 3. And if I run it, then I will have 3 principal components. Let's go back to the none option and connect this to the output as well to see the cumulative variance. If I run this, here is the principal component. Here is the variance explained by each variable. The first one has 73%. The second one has 23% almost. The third one has 3.7%. And the last one has 0.5%. And this is the cumulative variance of all variables. We can take a look at the cumulative variance graph as well. And choosing the optimal number of principal component is a bit of art and science. There is no single best method, but there are some common approaches. For example, explained variance. You can retain enough pieces to explain significant portion of the total variance in the data. It is simple and intuitive, but could be subjective as well. Another way is to use cross-validation. Select the number of pieces that optimize performance on a specific task like classification or regression. It is more objective, but computationally expensive. And we can use information criteria like AIC or BIC to balance the model complexity and goodness of the fit. It provides a statistical framework for model selection, but it can be sensitive to the data size as well.